So in this video, we will continue using the pre-filled template. So in the previous video, we have checked the basic types and their sizes. Let's move to the next cell. So the next cell is written load the necessary package. So for this exercise, we are only using plots. So we write using plots. Let's activate the cell. Once you get a green tick mark, it means that plots is loaded and ready to be used. Right below, you see a nicely edited cell. So that's the result of a markdown cell. And we're now going to plot a circle. So the equation of a circle is x squared plus y squared is equal to r squared, where r is the radius of the circle. The parametric form of this equation is x equal r times cosinus theta, y equal r times sinus theta. And theta is an angle in radians that varies over a full revolution. So theta should range between 0 and 2 pi. Let's use this information to plot a circle. So we do that in the Julia code cell just below. Let's first define theta using a line range as we used last week. So we define a line range and we want theta to vary between 0 and 2 pi. So we can type 0, 2 pi. We need to set the number of points. Let's say 100. Then we need to define the radius of the circle, r. We set it to 1. Since we know theta and we know r, we can compute x and we can compute y. So x, now, it's going to be a set of points. So theta is a range. It's a list of values. It's not a single value. It's a list of values that range from 0 to 2 pi. And there are hundreds of them. For this reason, when we type the formula, we can type r cosinus theta. But since theta is a range, we want to use a point here. This means that the function cosinus is going to be broadcasted over the whole array here. The same here, we set a point in front of the multiplication. So as a result, x will become also a list of points. Y will be equal to r sinus theta. And the last thing we want to do is to plot x, y. So you see something that resembles an ellipse rather than a circle. So this is because the default coordinates are not equal. So you have a larger distance to make for a length of 1, the distance in x is larger than in y. So in this plot, we will set the aspect ratio is equal to 1. Now it's a circle. Remember, this is the label of the plot. So let's give it a label that would make sense. We put a string there. So now we use the double quote. Let's press play. We have a circle. And now we just need to indicate x and y on the respective axis. So we type x label is equal to x and y label is equal to y. There we go. We have all the information. Next code cell is basically the same exercise, but we will see a cool feature of Julia. It's the possibility to introduce Unicode characters inside the code. So let's copy paste this here. So I'm copy pasting the code here. And there is this variable, which could simply be the mathematical symbol. Remember the code cell here, theta, is a Greek letter. To manage this, in Julia, you just have to press the backslash. You start typing the name of the Greek letter, theta, and once it's proposed to you, you just click it. And now you have a beautiful theta. We have a pi here, and pi is also a Greek character. So what about replacing pi by backslash pi? Agree? And you have a pi. Now we just have to propagate theta because it's being used here and there. No, that's the first step to make your code look better. If everything went fine, everything should still work. So let's increase a bit the complexity. We go to the next exercise, and now we're going to draw an ellipse. So there is the equation of the ellipse written here. And the parametric form of this equation can be formulated such as x is equal a times r times cosine theta, and y is b times r times sinus theta. Again, theta is an angle that varies over a full revolution. We can go fast and just copy the code from the circle with the nice Unicode symbols. And what we need to introduce now are two new parameters, a and b. So let's set a is equal to 2 and b is equal to 1. Now we need to change and add a in the definition of x. So we add a and b to the definition of y. Let's plot, and yes, we get an ellipse, and you see that the long axis, which corresponds with the x axis, has a major, the major axis is 2, and the smaller one is 1. We can update the label, and there we go. The last thing to do in this exercise, we go increase again a little bit the complexity. We don't want to plot only an ellipse, which will be which will have a long axis that corresponds with the x-axis. We also want to rotate it. So we are going to plot a tilted ellipse. To plot a tilted ellipse, we still use the same basic equation of an ellipse. Remember, the coordinate x and y are defined this way. And now we are going to cast them into a vector. So x is a vector that contains x and y coordinate. Theta is still an angle that varies between 0 and 2 pi. And we will need to define an angle of rotation. So the angle alpha will be the angle of rotation. In 2 dimensions here, we introduce the rotation matrix. The rotation matrix has 4 entries: cosine alpha, minus sine alpha, and cosine alpha. Let's now manually apply the rotation matrix to the vector x in order to obtain the rotated ellipse coordinate x prime. So x prime is r times x. This is a matrix vector multiplication, and the result here is a vector. This is the transform coordinate. So let's start again from the previously working example. So this just plots a non-tilted ellipse. Let's define now an angle of rotation. We define here alpha, so let's use the Unicode character alpha. We type backslash RLP, and now it's proposed. Click on it. And let's say that the angle of rotation is pi divided by 3. So we type backslash pi, enter, divided by 3.0. So now we have defined the angle of rotation. And we now want to code this relation here. So we need to define x and y coordinates of the rotated ellipse as a function of x and y of the original ellipse. So we are not going to touch these ones. These are the coordinates for the original ellipse. Instead, we are going to define new ones. Let's use x1, and we set x times cos alpha minus y times sinus alpha. Let's do the same for y. So y1 is x sinus alpha plus y cosine alpha. Please note that here I have put no dot between the cos and the alpha. It's because alpha here is a scalar value. It's just one value. So we don't need to put a dot here. We need to put a dot when we apply cosine to a full vector, a full range of values, like here. Here it's not needed. So let's plot x1 as a function of y1. And there you go. We get a tilted ellipse. Let's update the label. And I think we are good for today. Thanks a lot for your attention.